The topic of the video is the time-dependent perturbation theory in quantum mechanics. For a quantum mechanical system, if the Hamiltonian h is equals to h naught plus lambda into h sub p of t as equation number 1, where where h naught is uh, the exactly solvable Hamiltonian of the system with solutions given by u sub n as equation number 2 with energies En for those states, and the h sub p which depends upon time is called the perturbation Hamiltonian of the system. Then we say that we have the case of the time dependent perturbation theory if you have this kind of Hamiltonian. And the thing is that the Schrodinger equation for the total system, which can be written as equation number 3, where psi is the state function of the total system with the perturbation, then we actually take the solution psi as a linear combination of solutions of the unperturbed system, or the exactly solvable system UNs, and then exponential minus I omega n t or h cut with some coefficients or constants which change as function of time a and t as a and we can call this as equation number 4. If you plug in this equation number 4 in equation number 3 and do the differentiation, then the differentiation for a and t is written as a and t a dot over it, and then when we do the differentiation for exponential, we get this minus I by h cut into En, and on the right hand side we can keep or we can substitute the expression for h like this, and we can write the psi as a summation like this. So on the left hand side we have this a and t dot, and then we can write this second term like this, and on the right hand side when h naught operates upon these uns, we will get en into un, and then when h sub p goes inside to operate upon un, then we get this expression, and we can notice that the first term on the right hand side and the second term on the left hand side are equal, so they get cancelled. So if you write the remaining thing, we get this summation on the left, and then that summation on the right hand side. And if you actually kind of multiply this expression by um star on both sides and integrate over all space, that means for x, y, and z between the limits minus infinity to plus infinity, then we can get on the left hand side this integration with um star and un d tau, and on the right hand side we get this. But if you make use of the fact that this integration will be only integration um star into un d tau will be equal to 1 only when m is equals to n, and it will be equal to 0 when m is not equal to n. That is because these um and un are orthonormal to each other, and it is the case for any pair of these things. So we can write the left hand side like this. In the left hand side we get contribution only when n is equals to m, and in the right hand side we can actually write this e and t outside, and we can have this integration um star h sub p un d tau, which we can actually use this shorthand notation as h sub p square bracket sub mn. Then we can get this expression for am of time t dot like this. And if you keep only this am dot t on the left hand side and send the remaining terms toward the right hand side, we get this exponential I into em minus en or h cut into t, and if you call that as omega mn, I mean if you call this em minus en or uh, h cut as omega mn, then we can write this as this exponential here. And if you make use of the fact that these AMs or AN, I mean these AMs or ANs can be expanded as powered series in the parameter lambda, then we can write this like AN0, I mean ANT can be written as AN superscript 0 t plus lambda into AN superscript square bracket 1 of t plus lambda square into an2t, etc. And the same thing can be written even for am, that is amt is equals to am0t plus lambda into am1t plus lambda square into am2t plus etc. Then if you substitute these expressions in this expression over here, then we can see that am0 dot t plus lambda into am1 dot t plus lambda square into am2 dot t is equals plus etc is equals to 1 over ih cut into this summation lambda in place of an, this power series, and then the remaining things yes sub b mn and omega exponential I omega mn t. So if you call this expression as equation number 5, and in this if you compare the coefficients of lambda power 0, we can actually get am dot 0 of t is equals to 0. So we can actually set or we can actually say that all AMs AM zeros will be actually constants, and we can choose conveniently that one of these AMs which is AN0 is 1, and all other ANs or AMs will be 0. And if you compare lambda power 1 terms on both sides of equation number 5, we can get am1 dot t is equals to this expression. And in the summation, when we actually make use of the fact that an1 or an0 of time t will be 1 and other ans are zeros, then we'll get this on the right hand side. So and if you write this am dot t as a d by dt of am1, then we can get this expression. And if you send this dt towards the right hand side, and if you integrate between the times t is equals to 0 and t, then we can get this equations here. And when when we substitute for the limits, we get am1t minus am0 as this integral on the right hand side as it is. And if we choose this am1 at 0 time as 0, then we can get expression for am1t is equals to 1 over h cut into this integral as equation number 6. So in the first order approximation, amt is written as am0 plus lambda into am1, and this am1 modulus square actually gives the probability of transition of the system from level n to level m. That's it in this video, and thanks for watching.